In the previous screencast, we talked about that we can have compounds that are aromatic or anti-aromatic or non-aromatic. Okay, and then I said in this screencast, we're going to figure out how to identify those. So basically, we do this using the Lewis structure and Huckel's rules. Now, Huckel's rules for aromaticity were proposed by a German physicist and physical chemist named Erich Huckel. He lived from 1896 to 1980. And basically, if a species possesses a pi system consisting of p orbitals that are fully conjugated around a ring, then the species is aromatic if the cyclic pi system contains an odd number of pairs of electrons. And those numbers are called the numbers of electrons are called Huckel numbers. Or anti-aromatic if the cyclic pi system contains an even number of pairs of electrons. These numbers are called anti-Huckel numbers. Right? And so an example of Huckel numbers would be 1 pair, which would be 2 electrons, right? Or 3 pairs, which would be 6 electrons, or 5 pairs, which would be 10 electrons. And then anti-Huckel numbers, right, are the even numbers. And so that would be like 2 pairs, which is 4 electrons, right? Or 4 pairs, which would be 8 electrons, or 6 pairs, which is 12 electrons. So again, this applies to things that are pi systems consisting of p orbitals that are fully conjugated around the ring, okay? And that would also be planar. So maybe. Okay. Sorry, if that broke up there, I think I hit the wrong button. But like I mentioned, for a ring of p orbitals to be fully conjugated, the atoms that contribute to those orbitals must lie entirely in the plane. So we've got to be a ring, we've got to be planar, and then we have to have a certain number of electrons. Huckel's number corresponds to 4n plus 2. So sometimes this is referred to as the 4n plus 2 rule. Where n is any integer greater than 0, all right? So 1, 2, 3, and those are the Huckel numbers. And so you can also look at this, right? So for example, if we look at times 1 plus 2, that's 6 electrons, right? So that tells us that 6 electrons would lead for that to be aromatic, okay? And so we can use 4n plus 2 to correspond to the Huckel numbers, okay? Now, Huckel's rule applies to benzene, cyclobutadiene, and hexa-1,3,5-triene. Both benzene, shown here, and cyclobutadiene here have a fully conjugated ring of p orbitals. You can see those here and here, because every carbon lies in the same plane and contributes a p orbital. Okay, so we're planar. Benzene's pi system consists of 6 pi electrons. So there's 2 pi electrons for each of the 3 double bonds, and that's a Huckel number. Whereas cyclobutadiene's pi system contains 4 pi electrons, and that's an anti-Huckel number. Okay, so 6 pi electrons, Huckel number. 4 pi electrons, anti-Huckel number. So benzene then is aromatic. We are planar. We have 6 pi electrons. aromatic. Cyclobutadiene is what we consider anti-aromatic. Okay. Now, look at hexa-1,3,5-triene. This pi system, so this is a pi system, but it is acyclic. Okay. So even though the pi system contains 6 pi electrons, because it's acyclic, it's considered non-aromatic. Okay. So if something basically, let me back up. When we apply Huckel's rules to other species, it can be really helpful to take advantage of connections between resonance and conjugated pi systems. So each atom over which electrons are delocalized by resonance contributes a valence p orbital to the same pi system, and all of those p orbitals are conjugated, and then the number of electrons occupying that pi system is the same number of electrons that are delocalized by resonance. So that's where some of the connections are. But I want you to notice something here, right? If we have a fully conjugated ring in both of these situations, both of these guys are planar, then it really comes down to the Huckel number, whether it's going to be aromatic or anti-aromatic. If something is like linear or not planar, a lot of times we just consider that as non-aromatic, okay? And so the Huckel number is, to really use the Huckel number, the first question you need to ask yourself is it planar and is it a ring? Okay. So let's talk more about using the rules of resonance, which I'm hoping will help us with kind of what I was trying to explain previously. So if you want to combine the Huckel's rules with the rules of resonance to figure out if something's aromatic, anti-aromatic, or non-aromatic, here are some ways to solve those problems. Okay. Draw curved arrows to represent electron movement via resonance. So when you do this, it's really helpful to try to maximize the number of electrons being moved at once, right? Which is why when we think about benzene, a lot of times structure, as we talk about resonance, can be moved around like that. We don't do it one at a time, okay? And then try to move the electrons around a complete ring. Next, you have to determine whether the species has a cyclic pi system. If the electron movement represented by curved arrows in step 1 involves all the atoms in a ring and the ring is planar, then the species has a cyclic pi system and you need to count the number of electrons in the pi system. So, if all atoms in a ring are involved in electron movement, and the ring is planar, then the species has a cyclic pi system, and you need to count the electrons involved in the pi system. Right? Okay. If the species does not have a cyclic pi system, it is non-aromatic. So, if the species does not have a cyclic pi system, It's non-aromatic. Okay. Then you need to count the number of pi electrons using the curved arrows you drew in step 1. If the curved arrows correspond to a Huckel number of electrons, that odd number of pairs, then the species is aromatic. So for example, for benzene, where I drew up there, that's 6 electrons, which corresponds to 3 pairs, right? And so that's a Huckel number. So I can say, hey, look, benzene is aromatic. You know, and I've only taught organic chemistry for a bazillion years, and I still have a hard time spelling aromatic. If the curved arrows correspond to an anti-Huckel number of electrons, which is an even number, then it's anti-aromatic. Otherwise, right, the species is non-aromatic. And that case specifically would deal with unpaired electrons, which if you took an advanced organic class, that's where we would talk about the unpaired of electrons. So let's use the rules of resonance to assess and look at some examples of aromaticity. You can see how these rules are applied to benzene, cyclobutadiene, and hexa-1,3,5-triene, which we've already established are aromatic, anti-aromatic, and non-aromatic. You can see how the arrows are drawn, right? You can see here that all 6 atoms are involved and the ring's planar, so the pi system cyclic, and those curved arrows represent 6 electrons, and that's a Huckel number. Here, right, we've maximized our number. It's planar, it's a pi system, but we've got 4 electrons, that's an anti-Huckel number, so it's anti-aromatic. Here, right, we've got 6 atoms involved, and so, but it's not a ring, so it's non-aromatic. And so you can see how those steps can help you figure out if something's aromatic, anti-aromatic, or non-aromatic. Now, maybe the burning question in your heart is, Dr. Pierce, we've only looked at things with carbon and hydrogen. Can other atoms also be involved in aromatic compounds? And the answer to that is yes. So when we look at this figure, these are some examples of heterocyclic aromatic compounds. And they're named that because they have a heteroatom as part of the ring. In all 3 cases we see here, the curved arrows show electron movement involving every atom of the ring, and the ring's planar. So all 3 of these compounds have cyclic pi systems, and each pi system contains 6 electrons, and since 6 is a Huckel number, all 3 of these compounds are aromatic. Notice that the curved arrows depicting electron movement for pyridine here do not include the lone pair of electrons on nitrogen. This makes sense when we look at the orbital picture here, where the lone pair of electrons occupied the sp2 hybrid orbital, and it's perpendicular to the pi system. And so the next one is pyrrole, which is in contrast to pyridine. And when we look at the lone pair on pyrrole, it is included in the electron's movement. And the nitrogen-hydrogen bond here is what's using the nitrogen's sp2 hybrid orbital, leaving the lone pair free to join the p system. This makes sense for us too, right? Because of how hydrogen is an s orbital here, and we're forming a sigma bond. So it's going to come out like this, and the electrons are going to be here, okay? And then in furan, which we see here, notice that a curved arrow is drawn from just one of the 2 lone pairs on oxygen and furan, and the corresponding orbital picture for furan, shown here, shows that one lone pair is involved in the pi system and the other is isolated in this sp2 hybrid orbital. So that's the way that we would treat these different heterocyclic aromatic compounds. Now, let's talk about ions for a little bit, because molecular ions can be aromatic or anti-aromatic. So if we look here, the curved arrow involve every atom of the ring, and rings are planar, so each of these species has a cyclic pi system. The cyclopentlyl dienyl anion and the cycloheptatrienyl cation here each have 6 pi electrons, and that makes them aromatic. The cyclopropenyl anion, by contrast here, has 4 pi electrons, and that makes it anti-aromatic. So each of these have a cyclic pi system and are planar. So let's do an example, okay? Determine whether the species is aromatic, anti-aromatic, or non-aromatic. You assume the molecule is planar. So the very first thing we're going to do is we're going to see if we can draw curved arrows to represent the movement of electrons completely around the ring. And so I am going to do this just on the image above, where these electrons can come here. When those electrons come there, those electrons can be there, and then those electrons can be there. Okay? And so the next question says, does the molecule have a cyclic pi system? So the ring's planar, and all of the atoms of the ring are involved in electron movement drawn. So either the arrow is starting, right, or ending. So the molecule does have a cyclic pi system. And then how many electrons are in that system? So the 3 curved arrows represent the movement of 6 electrons, right? And 6 is a Huckel number, so the molecule is aromatic, right? Now, notice that for the ring to be aromatic, that external carbon-carbon bond here is treated as a separate pi system, okay? So this is an aromatic molecule, and we just ignore those 2 pi electrons with our count. Now, we can also have aromaticity in larger rings. Benzene and cyclobutadiene are monocyclic hydrocarbons with carbon-carbon double bonds and carbon-carbon single bonds alternating around the ring. And so those molecules belong to a class of compounds that are collectively called anilines. And so these are monocyclic, meaning one ring that contain only carbon and hydrogen, and they have alternating single and double bonds. They commonly are named in brackets aniline, where N is the number of carbon atoms in the ring. So cyclobutane is 4 aniline, benzene is 6 aniline, right, with the brackets there. And so you can have much larger ones, like here, because aniline of any size can be drawn, and then we can apply Huckel's rules to determine whether a particular aniline should be aromatic or anti-aromatic or non-aromatic. When doing so, however, we must take geometry into account, because remember, Huckel's rules require everything to be entirely planar. And so if you look at cyclo-octa-1,3,5,7 tetraene, which is also called aniline, it should be anti-aromatic if it were planar. But because of the instability that's associated with that anti-aromaticity, 8-aniline really resists that planarity. It really resists being planar. And so the ring's large enough and flexible enough that it allows the molecule to become non-planar. It kind of bends up. And so this is called a tub shape. It'll form a tub-shaped molecule here to kind of so that it's not in the anti-aromatic configuration where the p orbitals aren't all parallel to each other and it's not fully conjugated. And so we then characterize 8-aniline then as non-aromatic because it is not planar. It bends out of the plane, which is wild to me. But like benzene, if we talk about 10-aniline, right? 14-aniline or 18-aniline, all of those have Huckel numbers. of pi electrons, right? They're going to have 10, 14, and 18. And so those rings can be made interplanar, and they're all aromatic, right? But what we find, right, is that for whatever reason, the 10 aniline is still unstable, right? Whereas 14 and 18 are stable. So it also kind of bends out of plane, which is just interesting. In case you're curious about where a natural source of cycloocta 1357 tetraene 8 aniline comes from, it's produced by a species of fungus, and it can be used to synthesize polyacetylene, which is a conductive organic polymer, which is kind of interesting. Now, polycyclic compounds can also be aromatic. Biphenyl, which is shown here, is a somewhat straightforward example. It consists of two separate benzene rings connected by a single bond. And although the two rings are conjugated to each other, each pi system forms its own ring with 6 pi electrons. And so each essentially behaves as an independent aromatic system. And notice the curved arrows depicting electron movement via resonance also suggest two independently behaving pi systems. Naphthalene, which is shown here and is the active ingredient in mothballs, and anthracene, shown here, contain 2 and 3 membered fused rings. And these rings are considered fused because they have bonds in common, right? So this is separated by a single bond, that's fused, and these are fused. These molecules are also aromatic, and they're a group of molecules that are called polycyclic aromatic hydrocarbons, which are abbreviated as PAH. Okay. Like benzene, each of these molecules is planar and possesses a system of conjugated p orbitals that form a single loop and contain a Huckel number of pi electrons. And so they contain either 10 in the case of naphthalene or 14 in the case of anthracene. Now, let's look at another example, and let's do an example here of a fused ring. So when we look at this example, it's saying, is the compound shown here aromatic, anti-aromatic, or non-aromatic? Explain. Well, when we look at this, first off, let's ask our question, does the molecule contain a cyclic pi system? And how can we tell? Well, we are going to draw the resonance structure. So remove this bond here, and then we can move this bond here, and then we can move that bond here, and then we can move that bond there, and then we can move that bond there, okay? And so the answer is yes, right? When we draw the curved arrows with the maximum number of moving electrons, all 10 carbons are involved. And so those 10 carbons are going to make a complete ring, and that molecule's planar. So the molecule has a cyclic pi system. So then at this stage, how many electrons does that pi system contain? Well, we know that it contains 10 electrons. Those are the number of bonds that moved. And so 10's a Huckel number, so this molecule then is aromatic. And that's it. So that for us ends chapter 14. The next chapter that we'll pick up is chapter 24, where we will start to begin to look at reactions of aromatic compounds.